This video will be about improper integrals. An improper integral occurs when funky things happen, basically. And one of these cases is called a discontinuous integral. In a discontinuous integral, what happens is you have the integral of a function f of x dx going from a to b, except f of x is not continuous for the closed interval from a to b. So one case in which this can happen is if f of x is continuous from a to b except not including the point b. When this happens, to evaluate the integral, what you can do is replace your number b with a parameter, we'll just call it t, integrate as usual, but since you can't actually replace t with b, you can just take the limit as t approaches b. And since our interval is a, b, and we're approaching b from the left, then we're going to have to take the limit from the left, because otherwise the limit would not exist. Similarly, in another case, if we have that the function is continuous in the interval from a to b, but not including a, then what we can do is we'll replace a with our parameter t, integrate as usual, and then just take the limit as t approaches a, except this time, remember that we have our interval a, b. We're approaching a from the right, so we're going to take the limit from the right. And a third case is where we're taking the integral from a to b, and there's some point c where c is between a and b, and the function f of x is discontinuous at c. Then what we can do to evaluate the limit is just do the sum from a to c, the integral, and then the integral from c to b, and just add those together. And so that'll put these two integrals each into a form of one of the first two cases that we just mentioned, and we'll just take the limit as t approaches c from the left and or right. Another type of improper integral occurs when you're integrating to infinity or negative infinity. So for example, if we were integrating from a to infinity of a function f of x dx, then the way we would solve that is we would just integrate as normal from a to some parameter t, we'll call it. And then similar to what we did earlier, we'll just take the limit as t approaches infinity. Same thing with negative infinity. If we're going from negative infinity to some number b, then we'll just take the limit as t approaches negative infinity of the integral t to b of f of x dx. And lastly, if we want to go from negative infinity to infinity, we're going to have to choose some random number c and take the integral from negative infinity to that number c and add it to the integral going from c to infinity. Now c can be any number you want it to be, and usually you try to choose something that'll make the integrals easier to evaluate. Now when you try to solve these improper integrals, if you find that the value does approach a real number, then we say that the integral converges. Otherwise, if it seems to be reaching infinity or negative infinity, then we say that it diverges. So an example of a divergence would be, say, if I had an exponential function, like e to the x, and I was integrating from negative infinity to infinity, well, clearly the function is just getting larger and larger as I go out to infinity. So that integral we would say it diverges because it doesn't seem to come to any real value. It's helpful sometimes to know whether or not an integral diverges or converges, and sometimes a comparison test can be useful for that. So a comparison test works when you have a function f of x that you know is less than another function g of x for all values of x. Now we'll consider the integral from some number a to infinity of f of x dx, and we'll also consider going from a to infinity of gx dx. I'm going to represent this integral with the symbol a, and I'll represent this integral with the symbol b. So what we can say is, if we know that a diverges, then it must follow that b also diverges. Also, if we know that b converges, then we know that a also converges. However, we have to be really careful here, because it is not true that if a converges, we can also say that b converges. B could converge or diverge. We don't know anything about it. Similarly, if b diverges, then that doesn't tell us anything about a. Now this makes sense because if this diverges, where f of x is smaller than g of x, then if you're going to be integrating something even greater than that, then clearly that would also diverge. And you can use the same line of reasoning to figure out that if b converges, a also must converge because it's even smaller than b.